Hi, everyone. Welcome to the 100th episode of the Into the Impossible podcast. I am your fearful host, Professor Brian Keating, and today it is an exceptionally important milestone in addition to the 100th episode, but it is the first time that we are having on a real live Nobel Prize winning experimental astrophysicist on this podcast. And our guest today, Barry Barish, is fitting because he's been a mentor to me, and I try to act as a mentor to my students and those that I get the privilege of interacting with, both at UCSD and around the world, from the South Pole to South Africa to South California to all points and places in between. And I hope that you enjoy these very interesting interviews that I get to do with thought leaders and other people around the world. But this one is very special. Barry is an avuncular figure, is a mentor, and is somebody who really represents a role model to me and to literally millions of people around the world. We spoke today for a nice episode that's slightly over an hour, and it's just chock full of nuggets of wisdom that only Barry can provide, including what it was like to think about his career being over when the superconducting supercollider was canceled in 1993, to the stunning turn of events that led to his Nobel Prize only because the superconducting supercollider was canceled. We get into that and other details, such as what it's like to see Albert Einstein's name in a book that you get to sign. And finally, one of the most interesting tidbits of any of my guests on this past 100 centenary episode of the Into the Impossible podcast, Barry describes his battles that wage even till this day with the imposter syndrome. And I think it's quite startling and amazing and revealing in its vulnerability that even a Nobel Prize winner can feel the imposter syndrome and be afflicted with it more or less his whole life. And I think that really serves the purpose of what I'm trying to do in this podcast, which is to humanize these maximum minds of our multiverse of ideas. And these people that I get to have the privilege to interview really reveal themselves in a way which I'm hoping is unique. And I hope that you too will enjoy it and come along with me as we go further and further into the impossible and the survey, like Alexander the Great. Hopefully I won't weep for the lack of discovery of new intellectual worlds to conquer as I try to recreate the work of Alexander the Great. Maybe I'm Alexander the Mediocre. But in any case, I wish that you will continue on this journey. Please do subscribe. I read every review on iTunes, every comment and critique, helpful or not, on YouTube. I try to do that as well. So I want to express my sincere gratitude for all of your support, the listening audience and the viewing audience. You really make this possible and inspire me. And I hope that these guests inspire you. So please sit back and enjoy this episode with the one and only Professor Barry Barish of Caltech and the University of California, Riverside. You'll find out why Barry made the move there in just a second. Enjoy this episode.
Any sufficiently advanced technology is indistinguishable from magic.
And I want to start with how you, Barry, got to be involved in LIGO. It all started in 1994 after the cancellation of the superconducting supercollider. You were involved with that very deeply.
Officially, but I was actually in Caltech, my whole career, other than getting a degrees in Berkeley, have been at Caltech. And the one unique thing about Caltech is it's basically a zero growth institution. It's within 10 or 15% the same size as it was when I came, and I lost all my hair in the meantime. So the question has always been how you stay at the forefront of science without growth. It's a difficult problem. Caltech doesn't have a wonderful formula for it, but I think the underneath scheme is that no new appointment, whether it's from a retirement or somebody just leaving, belongs in any particular area or at any particular individual. So we always, basically, it's a completely open search. And which means that there's a lot of discussion about what areas we might go in or what individuals we might attract and so forth. I started on the Caltech faculty the same year as my colleague Kip Thorne. And so we've been good friends since the opening receptions and stuff you go to when you start on the faculty. And I was interested in his work on gravitational waves, which was purely theoretical and general relativity from the early days. But then at some point, we talked about whether and when to try to get such an effort at Caltech itself. And I was against it in the early days because I didn't like the technique. The technique that was being pursued was what are called resonant bars. And it turns out there's a long history in that, which I won't go into, but that's not the point. The point is, technically, I thought it was a bad idea because if you have a big bar, it's a great big bar of aluminum, and that big bar gets excited by basically a gravitational wave going through it, changes its shape a little bit, and if your sensors are good enough, you can sense that change in shape. But I think any of us know if you walk up to a big bar of metal and you bang it, it rings at some frequency. So that the bar has this feature that it likes some particular frequency and not other frequencies. And it's usually around 1,000 hertz and for a big bar of aluminum. And the problem I always felt was why would gravitational waves pick to be at 1,000 hertz that you really wanted to search broadband? And so I didn't like the technique, even though I followed it from the very early days. And although it was pursued by a scientist who was very good technically and had good ideas, but was not a very good scientist, so he thought he discovered, or maybe he wanted to discover too much gravitational waves. So there was a sordid history, but it didn't involve me. I was in particle physics, so I was more involved with Kip and the fact that it was the wrong technique. When the alternate technique, which we used, which is kind of behind me, an interferometer emerged, I liked it immediately because of the fact that it's broadband. Basically, there's nothing that picks one frequency over another except where you're able to work technically. And so in our case, we work on the Earth's surface. And on the Earth's surface, the evolution has been pretty good at picking where you can work. And so our ears, we communicate with each other in what we call the audio band, where we can talk to each other. And that's because the Earth is much too noisy if you go to lower frequencies. Animals go a little bit lower, but not much. The Earth just shakes too much. And at the highest frequencies, you can't sample very well. So kind of like music, we go from 10 hertz to 10,000 hertz. And that's where you can work on the Earth's surface. But the same technique can be used elsewhere, like in space, and cover different frequencies. So to me, it was really the right technique if you could make it work well enough. And there was some promising work done early, some by Kip Thorne, by Ray Weiss at MIT, but in particular in Germany, where they had built a small test interferometer. And so the question came up when we were talking about making the early 1980s, making a new experimental appointment in our department. I kind of teamed up with Kip and some others to make that appointment be an experimentalist, or maybe two, in gravitational waves. So it wasn't me doing it. And from that day on, we attracted Ron Drever, and then we had a couple of assistant professors, but they didn't get tenure. It's hard to get tenure when you don't discover something and you're doing technical work. And that went on for kind of a decade of R&D, where Caltech was one of the players, but it was done at a lot of places in the world. And at some point, it became competitive with the bars. The bars kept becoming better and better. because you could make them quieter by cooling them to low temperature, and then they got quieter. But they still only worked at this, one frequency, or small frequency band. But so by the late 1980s or early 1990s, it was pretty clear to me that the future was with interferometers, and that you could, at least from the R&D that had been done, compete technically with making it as quiet. And so I was part of kind of Caltech when you have something that's pretty big and has a lot of resources. We had an oversight group. So I was on the oversight group of this, but I was a practicing particle physicist during this whole time. And then, as you said, I was working on the supercollider. I was co-leader of one of the two experiments that was to be done there. So I should have been discovering the Higgs boson, which was our great goal. But we didn't get canceled, but the collider got canceled. And neither my colleague Bill Willis from Columbia and I were the leaders of it. Decided to go on to CERN, where they were doing the same thing. Not the same thing exactly, but I mean the same physics goal. And at that point, it turned out that they wanted new leadership in LIGO at Caltech, and that's when I came in. It wasn't an approved experiment yet. I mean, it had been on the verge, but it wasn't funded.
How was it to leave the field that you had, grown up in, matured in as a scientist, came of age as a particle physicist? Was it scary to that change?
No, invigorating. Why would it be scary? I think the only reason that things get scary is if you're just so comfortable in what you're doing, which probably means you're not pushing yourself or doing anything very interesting. So I've always done different things. I've worked on designing accelerators. I've worked on all kinds of accelerators. I've worked underground on a very different kind of experiment looking for magnetic monopoles. And then I worked on the supercollider, but not on the accelerator, on the experiment where the big challenge was how you could we thought and it ends up being true, but not because I had the great insight, that the most sensitive way you could look for the Higgs boson was to look for the production of it to decay into two photons. That's a very difficult challenge because photons convert to electrons if you go through any material, and you need material to make detections. So there's this battle of making a good enough detector, but basically making it not have any material, or as little as possible. But anyway, changing to gravitational waves first, theoretically, general relativity is as kind of abstract as it seems, is actually easier than quantum field theory to understand for me as an experimentalist. I can at least write down the equations of general relativity and try to solve them. A quantum field theory is abstract because it has quantum mechanics buried into field theory, and it's very, very difficult. So as an experimentalist, you like to understand as well as possible and as deeply as possible the science that you're doing. Changing to gravitational waves didn't put me into a worse problem there. I mean, it's difficult to understand Einstein's equations, but I felt as comfortable or more comfortable than with quantum field theory. So that part was okay. Technically, I had followed it quite closely for a long time. There was nothing about it technically from my background that scared me. I know the challenges that we have, but I didn't think that I needed some 30 years in this field or something to be able to attack those. They're quite different. Fundamentally, they're different in that in particle physics, we've collided particles together for a long, long time on different kinds of accelerators, and there's all kinds of things that happen. And you look for something that happens on top of a lot of physics. So if you remember the discovery of the Higgs boson, it was a very tiny effect. They usually suppress the zero when they show it. A very tiny effect on a background, but the background is very well understood by a lot of physics that's been measured. And so you can look to see a small effect and see that it has statistical significance over a physics background. And that's comfortable in the sense that you understand what's there other than what you detect. But it's very limiting because the signal to noise can never, ever be made any better than what happens. And that's the problem they're dealing with now at CERN. So they discovered the Higgs boson, but pursuing the Higgs boson itself will take another kind of device in any real deep way. And in looking at what else is going on, they're limited by the fact that maybe they're missing everything because it's below physics that drowns it out. Gravitational waves is a different problem. We're not limited. There is no physics underneath. So we're completely limited by how well we can see a signal over technical background. And certainly dealing with technical things that limit you is I can reduce them. I can't reduce physics. And it's the reason why we've done so much better than, say, CERN after a big discovery. So if you look at, since the Higgs, they're really struggling to go past that. A lot of my colleagues work in that, and that's not because they're not smart and they're not doing great technical things, but it's because there's a fundamental problem. They're limited by the physics. In our case, we're not. We're limited by how much the ground shakes and how much RF pickup there is, all kinds of just technical problems, which we know how to make better. I mean, we've done pretty well to get where we are, but we know how to make it better. And each time we make it better, the signals stand out more and we see more things. So we've seen a lot since the discovery, which is only a few years ago. We have the feature that we're measuring an amplitude and not a power. And so if we make it twice as good, we see twice as far out, and that's 8 times as much of the universe.
I want to make a controversial claim that, from my vantage point, I remember very well Jerry Guralnick, my professors at Brown, in 1993 when the superconducting supercollider was canceled. It was like a wake on the particle physics floor at Brown University, where I was a grad student. But I want to make the controversial claim that perhaps it was good for you because A, it freed you up to do LIGO, and B, maybe a lot could happen between, say, the Nobel Prize that you received for LIGO and the Nobel Prize that wasn't received by those working on the Large Hadron Collider, which ultimately did detect the Higgs. Since the Higgs, the SSC was also designed to detect the Higgs, the Europeans detected it instead of the Americans, so maybe perhaps the Americans didn't get much of the glory. But none of the experimentalists got any of the share of the Nobel Prize for the discovery of the so-called Higgs boson. Unlike LIGO, where the experimentalists, with the exception of Kip, did win. The leaders did win. You and Ray Weiss win the Nobel Prize. So looking back serendipitously, maybe it was one of the best things that ever happened to you.
Well, I think those are kind of game playing. I don't know. But I think what you say is true in the sense that at least I like to think that we detected gravitational waves when we did, that partially because of myself. And that's measurably true because this was in competition with Italian, French collaboration and Virgo, who were approved in actually half a year before we were. And we were in a race to detect gravitational waves. It took them 3 years longer than us, even though it took us a long time. And they're still not caught up. And I think that's a lot to do with the way we approach the problem because they're using interferometry as well. And they had as much resources as we did. And they had some smart people, but I think we made some decisions that enabled us to do better. And they're not all due to me, but I think some of them are due to me, and some of them are maybe due to the atmosphere that enabled us to develop that way that I was at least partially responsible for.
When you look at the challenges of running a big project like this, like LIGO, as you say, this type of science is really classical physics. It's easy to understand, And yet, I wonder if at a personal level, if we get a little bit less technical, how did you feel on July 4th, 2012, when this announcement was made that the Higgs was discovered by two teams at CERN, knowing that you guys were years away, you and LIGO were years away, and maybe never would detect the signals that you were seeking? Did you ever feel at that particular moment back in 2012, before the Nobel Prize was awarded, that maybe I made a wrong decision?
Uh, no, I don't. Maybe it's my personality. I don't really look back that way. Maybe at some level, but it wasn't really very evident. I was in Melbourne, Australia at the time, the official, but they had 3 sigma before that. It was built because they had to build up the signal. So it wasn't as much of maybe a surprise. I was really happy for them. It's a lot of my close colleagues, and I think what I don't like, and I know it's one of the things uh, that you criticize in your book and so forth. I think the experimental feat was a big one, and the credit completely went to theorists that did something 60 years ago. So I think that I'm not just talking about the Nobel Prize, but that's an example of it. And I think that it's hard to do because in this case there wasn't one individual that you could pick out very well in the way it's done. But if skipping to a topic I know you love or hate or something, that if Nobel Prizes were given like the Peace Prize, that CERN or the experiments would have gotten a Nobel Prize. And in a sense, even at that time in 2012, I felt that many of my colleagues had gone there. They've done well. I mean, young people got tenure, and it's a big thing, and so forth. But uh, but it wasn't there wasn't any magic in doing it. It was just really hard. It was the technical development of silicon, using silicon detectors that enabled them to get the resolution you needed close to the vertex. Uh, we may have had trouble doing it earlier at the SSC because silicon was such a key in the final detection, if you actually look at it technically. We use silicon too, but silicon detectors weren't developed as well in the time when I was working on it. So it was new. Silicon detectors had been used to discover the top quark, and we grabbed it for the SSC, but they were being developed by physicists, not by industry. And what changed is silicon became something developed because it had other uses for circuitry and stuff by industry. And then it really changed in being able to get very low amount of material and very good spatial resolution that you needed on these detectors very close to the vertex.
What fascinates you the most about LIGO? Is it the gravitational wave aspect of it? Is it the technical challenge? Is it the black holes themselves? Is it the neutron stars? All of which has been discovered really directly for the first time.
My attraction to the field uh, is that I always thought, I mean, a discovery is a big thing itself, but I always thought that it represented a new way, a brand opening up a new way that you could do exploratory science. Uh, Basically, a new way to look at the sky using gravity instead of using photons. And that meant that we could look at the sky in principle to do a new kind of astronomy. Well, I'm not an astronomer, so that's great, but still, I can appreciate it. I always thought more that closer to your field, and I still don't know how to do it, that it's the ultimate way to study the early universe. The reason, of course, being that the cosmic microwave background is only good to look a few 100,000 years after the Big Bang. And if you want to look earlier, you need something that's not absorbed. I had been interested in that from the fact that earlier I worked with neutrinos. And I used to think that was the key, but the trouble is it's technically almost impossible, I think. This, although we don't know how to do it, it's not going to happen in the next few years unless something's really different than we expect. We look for it. We look for signals from the early universe, but we don't think we'll see them because we work at such high frequency. but I always thought that that was an attraction. I also thought there was another attraction, which again, I can only speak about romantically. Like the early universe, I can't tell you we can do it, but you said, well, why was I attracted? I think this is a general approach that eventually may give us the key to actually, because gravitational waves aren't absorbed, if we can see them directly from the early universe, we can see back to the first instance of the early universe instead of a few 100,000 years after. And we also, in another way, should be able to see something equivalent to the cosmic microwave background with neutrinos if you were able to do it. So both ways that is good. I also, as coming from quantum physics, have always felt that we should be terribly embarrassed as physicists that we think we understand physics, but we have two wonderful theories of physics: quantum physics, basically, or quantum field theory that explains almost anything that happens at CERN or when you collide particles together. And then we have another great theory called general relativity, which is great at relativistic effects and long distances. So we have a great theory at long distances and relativistic effects. We have a great theory at short distances, and never the twain shall meet. And somehow theorists have been working on how to bring those together for decades. And I always have felt that what we miss, obviously as a biased experimentalist, is the experimental clues to actually do it. That somehow thinking you invent string theory to do it or something may work, but I think it's much more traditional that we find clues. And so again, I don't know how to do it, but I think maybe the way to really study black holes is, for example, someplace where both worlds have to come together, might be with gravitational waves. So it looked to me, even beyond what I can see to do in the next 5 years, 10 years, 20 years, that it's just a new approach. So I was romantically attracted in these kind of ways.
My late colleague at Caltech, my mentor, Professor Andrew Lang, who was your colleague, used to say that part of making a successful experiment work is that you fall in love with it and you kind of lose all sense of rationality, at least at first. Because there's sort of an irrational attraction that happens in the beginning. Because I can't resist this, I had on Sir Roger Penrose last month, and I gently chided him. I said, all these figures in all these topics in Shelley Glashow's book, Interactions, which I discussed with Shelley Glashow recently, he talked about the way that theory and experiment, in the case of at least quantum gravity, which you just brought up, Barry, there's this kind of feedback cycle between theory and experiment that we often hear the same story, that we need to understand singularities in space-time because where they occur, namely in the Big Bang and also at the center of black holes, these phenomena seem to require the union of the very small with the very strong gravitational fields. I pointed this out to Sir Roger and to Shelley and to other people, that we actually don't know if there are such singularities. It could be that a singularity at the early universe's creation could be forever firewalled off from our observations, the same exact way that black hole singularities are firewalled off from our observations, as well as Sir Roger Penrose has described. So I asked Roger Penrose, and I'm going to ask you, who says there has to be a unification of quantum mechanics and gravity? Maybe it's just our prejudice that we want to unify things.
Yeah, I think you're right. I think, but as scientists, it's attractive enough to think that you develop a theory of physics that can describe physics, and you don't have two discrete ones that you can't somehow make talk to each other. And so it's attractive enough to think there must be a bridge between them, I think, that that it's worth pursuing. Can you really say that absolutely has to be the true path, the path to truth? I don't think so. I think Penrose is right, or you're right, or whoever says it, that it may be that that's a false direction. But searching for gravitational waves or cosmic microwave background, all these things that we do that haven't been seen before, we don't know absolutely. We wouldn't be looking if we knew absolutely that the direction is the right. So it has to be promising enough, promising in that it might be the right answer, and promising in that you can actually make progress.
Actually, Lenny Susskind points out that black holes' horizons are as interesting as the singularity itself, and they are just as quantum mechanical, he claims. Perhaps even more quantum mechanical, this event horizon and what he calls the stretched horizon, sort of like a firewall. And you have effects that manifest themselves at the Planck length above the event horizon that he claims will be visible someday with instruments not too dissimilar from LIGO. And it brings me to a question that Shelley Glashow wanted me to ask you, and that's about contributions to astrophysics with LIGO. And that this notion that you mentioned in your Nobel lecture last year, or rather in 2017, about the prospects of measuring primordial gravitational waves, which you did mention as sort of the ultimate, represented the ultimate achievement in gravitational wave science. And obviously, as you must know, I think experiments like the Simons Observatory will be hot on the trail of these primordial gravitational waves. But Shelley wants me to ask you about another form of gravitational waves, useful in cosmology, perhaps to solve the Hubble tension.
Well, I mean, we measure the Hubble constant, actually, and we have. It in a few years, I mean, if this remains a tension a decade from now, I think we'll resolve it. Basically, we have a way that doesn't rely on some, without going into the technical things, some of the biases of doing this ladder business and so forth. It's a pretty direct measurement that you can make and complementary with gravitational waves. And we have made a poor measurement of it that looks consistent with the whole thing. Yeah, but that means, we need 1,000 times more data or something to pursue that. I don't think we're limited by systematics, just limited by getting enough data. We can't get that much data by continuing just to run LIGO, so we have to make it better. We are working on making it better. I would say it's kind of to get enough data on our measurement, independent measurement of the Hubble constant to resolve that in a different way or get a third measurement. At the level that they're doing it and with the systematics that they talk about, is a decade away. But doable in LIGO, not a future instrument. I think the improvements that we have to do in LIGO, it's not like what I said about early universe or this or that, which is going to require a different instrument. But that'll be done with the improvements that we will make in LIGO.
Along those lines, Ray Weiss, he's coming on the show soon, and he wanted me to ask you a little bit on the technical side of things, which I could translate into our own language. And I'd like to know, of these two different properties, which would you want to add most currently to improve LIGO if there's no obstacle technologically or financially? And I don't think there is. Would you rather double the sensitivity of LIGO or add on polarization detection capability?
I think for me, I think the clear path, the clear reason for sensitivity, which is what I favor and what we're working the hardest on, is not what I just said for the Hubble, which is getting more data, getting enough data to resolve it, but basically being able to look further out, which is equivalent to looking at higher Z or higher redshift, which means that we can start to at least think that we can start to approach doing cosmology and not just astrophysics with gravitational waves. So when I say it's a new probe of the sky, right now it's astrophysics. But if we can get to larger Z, then we start to be able to do cosmology with gravitational waves. And to me, that's the biggest advance in the coming 10 or 20 years that I feel is the biggest driver romantically, is to start doing cosmology, something you love, of course, so you probably like that answer.
Yes, definitely I approve of that answer. If anything, you found it interesting, as Jim Gates has written a book about Einstein as well, and of course was one of the founding fathers of string theory. He was a postdoc at Caltech in your early days. He asked me to ask you about the prospects for finding perhaps scalar tensor evidence for scalar tensor vector gravitational waves in LIGO. I don't know if that's something about LIGO's potential capabilities that interests you.
It's of course it's interesting to Gates. That's kind of his thing, and we've communicated about it quite a bit. It's not my deepest interest because trying to look at alternate theories of general relativity to Einstein. I'm much more pragmatic as an experimentalist. The problem is when we look at different, I step back for a second, if we look at different theories in particle physics, whether you're looking at the Higgs or you start looking at different, more dynamical theories, in particle physics, we're able to make predictions and then compare them with the data. Okay. The trouble is, including Gates' work, in general relativity, what right now we're making some pretty damn sensitive tests of general relativity. For example, putting in a simple dispersion term in these detected many wiggles in gravitational waves in the merger of two waves. If we put it in a dispersion term in it, which is equivalent to putting in more generally something like a graviton, okay, then we can set a very small limit on it. But the spirit of what I'm doing there and the spirit of what I do when I'm testing general relativity right now is just looking more and more sensitively at the terms that Einstein's calculates and looking for a deviation. When I do something in particle physics, I'm used to comparing two theories, and one of them may fit the data well and the other one not. Here, I'm looking for some breakdown in Einstein. It's not satisfying to me to look for a breakdown in Einstein's theory. Therefore, there must be some alternate. The kinds of theories that Gates is interested in and other people are don't predict what we detect at the level that we actually can test in the data and compare with Einstein's theory. So theory is too far behind, I think, and not capable of making it attractive to me as an experimentalist. That it's a very unsatisfying kind of test that we do now.
May I ask you a question about the philosophy of experimental science? There is an aspect of Karl Popper's demarcation philosophy, which is that you should only pursue scientific things as those things that can be falsified. But I want to ask you a slightly different question on the experimental side. When do you stop an experiment? I mean, it's not like you know or for sure when you should kill an experiment the way you might kill a diseased worm, pet, or something like that. So you have to have a certain amount of judgment to know that it's better to turn off the experiment and move on to the next one than to slowly and slowly get better monotonically and just run experiments like CMB experiments forever. And the question is, is there any sort of criterion as Popper might have? Is there a Barish criteria, rubric that we can use?
It's a good question. I can answer it personally, but trying to answer it in a way that's not personally. I mean, I do what turns me on, kind of, which is not as deep as that. I think the general problem that we have, and why science, our kind of science, doesn't move forward faster than it does, is that the system is too conservative. We love something called peer review, but peer review is actually very conservative because we basically turn in proposals to do something to get funded, for example, if they're offbeat. I mean, the theorists can do anything they want and they throw it in the wastebasket, but you and I can't. We have to go and get some resources and we turn in a proposal. And if it's offbeat, it doesn't get all outstandings in the reviews done by peer review. So peer review is too conservative. And then if you get money, your money's private, but my money came from the NSF. The NSF is answerable to Congress. And so if you do something that doesn't, that is not very defendable, then you're not. So the NSF, something as wonderful as the NSF to support science, is far too conservative. We have to be able to tolerate failures, many more failures than we do. And experimentalists should be basically turned loose to follow our dreams. And I think science would move forward much more. Some of us would fail at things. We'd have a lot more fun. And I think we don't have to be so analytical about how we move forward. I've never kind of had that in what I've done. I mean, I spent a decade chasing magnetic monopoles and underground in Italy, and that was a problem that I was interested in high school. So, and it was nice to be in Italy, but I basically, before I worked on the supercollider, that's what I did. I spent 10 years in Italy chasing magnetic monopoles. But I could do that. It didn't take very many resources. Actually, the Italians supplied a good part of it. But that's the kind of thing that we should do. I would love, I like being a physicist anyway, but it would be better if I didn't have to be so goddamn conservative.
Yes, I think that's partially why institutions like the Simons Foundation and other private institutions like the Moore Foundation are more nimble.
Absolutely.
These private foundations are succeeding not only because they're supporting in projects like the Simons Observatory, but also because they can be more agile. They can take more risks, and they can take more rewards and do more experiments and get those experiments done early, even if that means failing. And so, have you heard this rule popularized by Malcolm Gladwell, but really based on this study by Anders Ericsson about becoming an expert? So, how do you become an expert? Well, according to Anders Ericsson, at least maybe apocryphally or not, you need to spend 10,000 hours doing a particular craft. So it turns out that he studied Bill Gates and maybe other people like the Beatles, for example, and he talks about this in Malcolm Gladwell's book, that the Beatles played about 10,000 hours worth of shows in Germany long before they ever got famous. People like Bill Gates had access to computers for 10,000 hours in their youth. That when the time came for them to apply the kind of unique amount of training they had done, they were well positioned to do so. And so I'm wondering about you, your opinion. Do you think that you need some specific skill set? Because it takes a lot of time to not only become expert enough in one branch of science, as you did with experimental particle physics to become a leader, and then to also apply it to lessons learned for a completely orthogonal branch of science, namely gravitational-wave astronomy. And I remember when you were here last year at UCSD, thinking about how do you make decisions on who to hire. It's not like you can say like, here, give me the pamphlet on how to run a super project like LIGO. And last year you told me, when I asked you for a shortcut for a hack, you said, sorry, Brian, there is no shortcut. So I want to ask you, how did you develop this skill set?
Well, I think, you have anything that you do in life, you have a combination of whether you have the right ingredients to do it. I probably have both the personality and maybe the analytical ability and so forth to do it, but I'm also humble. So when physics started to require a fair amount of resources, I think I mentioned this to you when I was in San Diego, I went and actually studied how you build a bridge and how you organize things, and read the kinds of books that they have. It just doesn't take very long to understand that there's a kind of organization to build a bridge that, look, the dangers in building a bridge are mostly that it's going to take too long and it's going to have technical problems. Maybe occasionally that it'll fall down, but usually the risk part isn't the big part. It's kind of carrying it out. So there's a little bit on the risk part, but that you do by over designing. That scheme doesn't work for what you do or I do. It was very clear to me. And yet aspects of it are essential to make sure that you can reach the goals that you want when it involves lots of people. So I was attracted, I didn't mention this to you last time, I was actually attracted to something that you may or may not know about, which is called the Skunk Works, Lockheed. And Skunk Works was named the Skunk Works because it was named after Little Abner's cartoon, where there was this was a 1940s cartoon, which had an old warehouse that smelled because it had what it had in it. It was called Skunk, S-K-O-N-K. And Lockheed, when they made the Skunk Works, which developed the U-2, for example, when they developed the Skunk Works, it was a guy named Kelly. And when he developed the Skunk Works, he called it S-K-O-N-K. And they he got sued by the Little Abner people, and now it's called Skunk Works, S-K-U-N-K. Well, that's the history. But what's in it, the idea of it is that they took a part of Lockheed and they broke it out and they left these guys alone and didn't require all the things that we were talking about in an organization, all the accountability and so forth. And to me, that had some of the ingredients that you want, which is that you bring people together and they interact and they have the freedom to pursue things that are different from just the straight paths and make bigger steps. So it's the closest I could come to anything, but it's wrong too for what we want to do. And it's wrong for a couple of reasons. One is that it's still a hierarchical organization, basically you and I live in physics departments, which have emerged after a long time to be a pretty effective place to do science. And that organization is completely flat. It's not hierarchical at all. There's a department chairman who probably can't tell you what to do, even if they try. And there's all these professors and they do what they want. And the only difference is now you have to bring it together to some sort of common goal. So it's important, I think, in trying to do what people have to do in building a bridge, but a highly technical bridge, first to not be, to mimic this totally hierarchical organization, which DOE tries to impose, for example, on the Dune project at Fermilab. The main problems in succeeding technically and in terms of the way an organization works are that there are two things I think are absolutely essential. First, it has to be done by scientists because there's too many scientific decisions. So having a bunch of managers doesn't work. So if you look at LIGO or you look at what we were doing at the SSC, all the key spots were scientific. Sometimes in the same box, if you want, you can put an engineer, but basically you're doing a science experiment, you need scientists. So you have to find ones that can live in this kind of environment. There's two things that I think are crucial, and I've worked on a lot of experiments. The first is that you have scientists, not engineers. We have plenty of really super engineers in LIGO, but it's a scientific organization. But the key to me, which is not there at all in Kelly's Skunk Works, is integration. So the big problem is, for example, in LIGO, we have the world's best laser people. And we have, we have a fantastic group of people who do controls and so forth. But how do you bring it all together to sing together as one instrument? And what that requires is not doing what is done in building a bridge. So the key flaw for us in taking that style is that they have a very important role that they call systems engineering. Systems engineer, if you go to JPL or something, is a guy who's a very well-trained engineer who does all these interface documents. Yes, which do one side and another side. It's just exactly the wrong thing. What you need for integration, and what we did in LIGO, is have the best scientists we can find have the job not of building some subsystem, but integrating. In our case, it was Albert Lazzarini was the chief one in LIGO. A very, very smart guy, very broad technically. And in anything where you had to bring two things together, you needed the controls and the laser to work together to run the laser or whatever it was. And somebody that did the interfaces isn't a bunch of diagrams. It's somebody that's able to make sure that these two sides work together and that the control system's going to control the laser in the right way and stuff. And so I think the biggest, so you can draw all kinds of diagrams and stuff, but I think the real key to success is integration. And the key otherwise is that scientists have to work on the different parts, and then you have to do something to kill or to mute the change control system that exists in an organization, because it again inhibits change. Anything that takes a long time to build, like LIGO, things, or even the CERN experiment, silicon, requires that you stay up to date if you want to do something that you couldn't do today, and it's going to take you a few years to do it, you want to be able to be as current and forward-looking as possible at all times. There's an inhibition against that when you have a formal system that requires you to go to a board and change it and all this kind of stuff, which is built into these standard organizations. So you need to have some variant of that, but it has to be, again, run by scientists. It has to have a mission that basically enables and encourages change, but it's responsible to make sure the change is worth doing, that it isn't a dream, that it's going to work, and it isn't going to increase the cost too much and so forth. But that's a practical part of it, but you should be assuming change. If you look at the LIGO we ended up with compared to what we took to the NSF in 1994, there's a lot of really big change. Even the laser itself, for example, the laser that existed in 1994 was a gas laser. I didn't like that from the beginning. I inherited that when I came in. And I always thought the future of this was solid state lasers. But at that moment, they weren't as good. They weren't being made commercially and so forth. And we switched very early to a solid state laser. It required a process that all the people that were already embedded that wanted to stay with a CO2 laser could buy off on afterwards. So we needed a process, but encouraging change and doing it responsibly is the opposite to having this big board that inhibits change and is great for making sure the bridge comes in that you build on cost and on schedule. So somehow you need to have the cost, monitoring costs. The important thing there is to make sure that it's not done by a separate group of cost people, but that it's inherent in the people, the scientists, again, that are running the guy that's responsible for making the laser has to be responsible for the budgets and it has to be translated to him in a way that he or she understands the budgets, and it's not just something that's bureaucratic.
Just to maybe push on this a little bit, I found it obvious that, in contradistinction to building a bridge, an experiment in research is something that you're trying to really figure out for the first time every time. In other words, there's no such thing as experimental bridge design, or at least I'm not going to be the first person to walk over your experimental bridge. But we often, as scientists, feel like we are somehow superior in a sense, that we know better than, say, a manager, on a project, an engineering project, or even on a science project, that we know quantum field theory, and therefore we don't need to learn how to manage people, how to run successfully, manipulate the resources that we have in terms of finances and time and maybe equipment, and marry those to this precious, extremely precious resource of human capital. How do we do that? There's no books, and yet there are, perhaps resources that we could employ. So I don't think we can do away with all these aspects and just be totally freewheeling and fancy free with our experiment. So I want to ask you, is there any sort of, at least, way that if you were a manager of a project like the Simons Observatory, what amount of effort should one put into, say, developing the best practices like change control?
The charter of the Change Control Board has built into it different than what it would have if we were building a bridge. That's what I was saying. And we have equivalent of systems engineering, but it's done in a way that is optimized for our own problem. We call it integration, but it's basically making sure that it's not done in the way that's done traditionally. So our organization might look superficially very much like, and in fact, it's a great trick because our organization looks like a standard organization, and the reviewers at NSF or wherever don't get shocked by the fact that it looks like a Skunk Works or something. It doesn't. It looks like a standard organization. It's just that we've basically changed the missions and who's in the boxes and what they're doing and so forth. So I really was maybe saying it wrong when we've taken what you call best practices basically and altered them in the way that is optimized for our problem, which is not the biggest problem in us. We have a problem of cost and schedule too. We have to meet budgets, but it's not the overwhelming feature. And the one that you talked about, the fact that technology, that we're at the forefront, so we're limited by technology generally, and the fact that technology can improve, or that we can make breakthroughs, or that we find new problems as we go along. We have to be able to change things, not change them because they cost too much, or change them because something didn't reach a spec, which is the way it happens on a bridge, but we change it because it's going to enable us to do our science problem better. Oh yeah, yeah, yeah. I started. My background is that I was born in Omaha, Nebraska. My parents moved to Los Angeles when I was about 10, and neither of them went to college, so I didn't have any real background. They were they were encouraging for education and being a professional, because it was a Jewish background that's kind of culturally built in. But I didn't have any of the advice, if you want, or encouragement. They didn't know anything. My father's worked on cars, and my mother was a housewife. And but I read a lot as a kid. I know you got interested in astronomy at a young age, but I didn't. I read science fiction. I read mystery stories because that's what my mother read. And then I got beyond that, and I grew up in Hollywood, kind of near Hollywood, East Hollywood, and so I was around a lot of what I would call storytelling, people that made movies and were into that kind of stuff. And I always liked storytelling. I liked writing, and I was always reading something. So I liked reading, writing, and so forth. And at about the age of 13 or 12, I discovered good literature. And so I really got into storytelling and being, or reading good books, the Russian novels or whatever you want. And so by the time I entered high school, I certainly thought that my life was going to be writing novels, or at least writing or doing something like that, and not science. I was always good at math and things, as we all are, kind of, to get that far, get what we are. But it didn't mean anything much to me. And when I finally was cured of trying to be a writer, I decided I didn't know very much, that I would go to do engineering. And so I applied to UCLA and Berkeley in engineering. I happened to graduate in mid-year from high school. At that time, they had mid-year graduating. And so I also had applied to Caltech. I had no vision to see beyond California. It's just, my horizon was too short. And so I applied to, and I was advised not to apply to Stanford, because at that time they were at least reputed by the advisor in my school to be biased against Jews. So I was told to not waste my time on that, but I did apply to Caltech, and I thought I'd go to Caltech because but I couldn't go in January when I graduated from high school. They took a class in September. I wasn't admitted yet anyway. And so I went to Berkeley mostly because it meant leaving home and not going across town, and started an engineering school in Berkeley. You had to take another test to be in engineering. And freshman engineering there consisted of engineering drawing, which I love now because you can visualize something. But doing it, I had this terrible course, and as a excited freshman, where I got criticized, as you said, for my arrowheads, and that turned me off. And then I had a second course in surveying, where you had this nice little transit and survey instrument and went around the campus and measured the heights of buildings and stuff. That was fun for about an hour while you learned about the instrument. And then I was a shy 18-year-old or 17-year-old, and running around, sitting on the campus looking through this little thing while kids walked by and kind of made fun of you, or I thought were making fun of me. It didn't appeal very much. And at that time, I had to take freshman physics, and they were making discoveries up at the radiation laboratory, and so I switched to physics. And then I got really lucky, because I switched to physics, and then I got assigned an academic advisor, and it turned out to be Owen Chamberlain, who got the Nobel Prize for the antiproton. And he invited me to come up to the radiation lab because I was pretty good in classes. I had extra time, so I used to go up there. Now the radiation lab, which is above the campus, has a little shuttle bus that goes back and forth. The antiproton was discovered in 1956, and they won the Nobel Prize in 1959, and this is the period right in between. So, he was busy as hell, I suppose. I now understand that the time between when we saw gravitational waves and the Nobel Prize was a pretty busy time too. But he was too busy and for me a lot of the time, but I had this overhead of going all the way up the hill. So I used to wander up and then they didn't have as much barriers for radiation problems and all that stuff. You could wander around. The Bevatron was too intimidating for me and nobody would talk to me. I was a little 17, 18-year-old kid. But I wandered up to the 184-inch cyclotron, which is the classic machine that existed there. And it was much smaller, and it had a guy in the control room who ran it, who at the time I didn't know who he was at all. It's years later I saw his picture along with Lawrence and Alvarez and all these people. He was always the guy with the white coat and stuff because he was their technical leader. His name was Jimmy Vale. But he was one person at the lab that would talk to me. So I wandered into the cyclotron, and he would talk to me, and he was running this machine, and he knew the art of running it. And that is the period when I actually learned about control systems, not knowing that that's what I was learning, because he would they would have oscilloscopes and then a lot of knobs because everything was analog at that time, not now. And so somebody wants to change the energy of the machine. And so there's a big knob that had energy. And I'd be there chatting with him, and he'd change that knob, and he'd also go tweak to something else, a little tweak somewhere. And I'd ask him why he would do that. And he'd say, because it works, basically. And, it's somebody that grew up with this machine, and it worked. And so basically I sat there and I used to chart what he did. So at first I thought I was charting it so I could do what he did. But eventually I learned that basically the control system wasn't diagonal. And so you have a matrix that's the control system. An ideal one is diagonal, and when you change the energy, you change the energy. But here there's some coupling between the energy and something else. And so the off-diagonal terms are a problem. And I remember when I had all this big insight and I showed him the matrix and the off-diagonal terms, because I had sat there and he didn't know what the hell I was talking about. And I didn't either, but I was arrogant, So that was when I really got into experimental physics. It was really through sitting in a control room. And then that's how I got involved in doing accelerators. Actually, I did it.
Yes, when we talked about that last year, that part of the motivation for having the 40-meter instrument at Caltech, you said that it was a training platform that gave your students, and even one of my former students, Darcy Barron, who's now a professor, it gave her hands-on experience doing low risk but potentially high reward science, that she could learn a tremendous amount of physics, experimental physics, and then be an asset to the project. And I know you only have a little bit more time, and I have a change control board meeting myself, but I want to ask you a couple of questions that come from your partner in crime, Ray Weiss. Ray will be on the show in the next few weeks, and he wants me to ask you about your thoughts for future upgrades with LIGO. And what kind of survey will you have coming up with that, and what's your vision?
I think you should have an interesting conversation with Ray, because he's really now the way he gets like this about how we get from here to there on what we call the Cosmic Explorer, which is the next generation. There's not a clean set of ideas about how long we keep improving LIGO before we change to a new detector. And then we have a second kind of issue, which is that in Europe, they were not constrained as we were to think about a next generation detector. And they did a design actually in 2011, supported by the European Union, I suppose, grants. And this is called the Einstein telescope. And when we had not discovered gravitational waves, the NSF wouldn't let us spend a penny or even breathe that we were thinking about, next generation. That we just had to accomplish. I mean, we did a little bit of thinking, but we couldn't really do any resources. So we've been, since we discovered gravitational waves, and the older generation like Ray and I can afford to worry about the future more than the young guys who should exploit what's happened, and they are. We've been working toward what we call the cosmic explorer, and the idea is complementary to the idea in Europe, although in the end, you really need to make globally something that's either the same or that makes a set of detectors around the world that are practical and right. But the big difference is that they designed the next generation gravitational wave detector that's deep underground. That gets rid of a lot of the shaking of the Earth problem. But of course, there's the big overhead in getting deep underground. It's triangular in shape, which I won't go into why that's good, but that's the way they do it for the space experiment, LISA. It's a triangle instead of a L shape. It gives you a certain ability to go both directions, to inside know something about what direction the gravitational wave came from and so forth. But it's, again, a big overhead in doing that. And lastly, and the thing that I think is the biggest next step technically for us, is to cool it. I mean, the obvious thing is to go to low temperature. It's not trivial. The problem is going to low temperature. We have these test masses which aren't supposed to move, and yet we're supposed to suck all the heat out of them as the laser beam goes through without making them move. And they're absolutely wonderful mirrors. The quality of the mirrors are the best super mirrors that exist, and the materials and everything matter. And the material that you use at low temperature is not the same as you use and we're not material scientists. So now we're working with material scientists and what to do and what's the right temperature to go to and so forth. So that's it. But the biggest overwhelming problem practically is that about a third of the cost of LIGO is the vacuum system. Not like the vacuum system I see behind your head. A big vacuum system that is a third of the price of LIGO itself. And now we're talking about the way to get 10 times the sensitivity is to make everything better, but also to make it bigger. So just stay on the Earth's surface, but make it 40 kilometers instead of 10 kilometers. We have to worry about the curvature of the Earth, but that's secondary. The big problem is that if something costs a third of the cost, and now you make it 10 times longer, it's the dominant cost. So how to make the vacuum system, which has to be big, it can't be little for a bunch of reasons I won't go into, and be high vacuum, which it is, and make it much cheaper than it was before, is the practical overwhelming problem. And my colleague Ray Weiss is wonderful at practical overwhelming challenges, and so he just pursue with him his ideas for how do you make a vacuum system and what tests have to be done and how we get the support. It's a little bit like you were saying before. How do we get the support to do the R&D on something that isn't a going project and so forth? Because you just know it's going to be the big problem, but you want to work on it now before we're proposing it. We're talking about being ready to propose, after CMBS 4 is done or something off the table. So we're talking about, the middle of this decade. We proposed it, started 2030, start building it. You'd like to have the next generation one operational about the time of the space one, so they were complementary. But so that's 2035 or something. But for us, we can worry about that because we have tenure and have done our. But Ray will sing all the ideas. That's an engineering problem. But what's wonderful is how much science goes into trying to solve an engineering problem like that. So how do you make a much cheaper vacuum system that's a super high vacuum system? We have the largest high vacuum system in the world. And how do you do that?
So before we leave, I want to conclude with some questions that I ask all of my guests. Barry, if you'll indulge me, it won't take very long. And the first one is based on a concept in Judaism called the ethical will, which in Hebrew is pronounced zava'ah. And it basically means something that you want to pass on to future generations, but not in the form of material wealth, but in ethical and wisdom-based wealth that you can bequeath to your intellectual, biological, and ideological heirs. As you know, Alfred Nobel did this as well when he included a requirement that the winners of the Nobel Prize would have to make humankind better through their inventions and discoveries, even the ones that were winning it in the sciences, such as yourself. So I want to ask you, what would you most like to leave in the terms of wisdom or ideology for future generations? Not only for your children and grandchildren, but for humanity as a whole.
Yeah, I, 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 I'm not going to be as philosophical. I'm going to be very practical and answer the thing that I think is singularly the biggest problem in that somehow maybe you and I evaded for lucky reasons, maybe different reasons, and in growing up. So I grew up in a certain family I didn't have, and so how did I get where I am? And who didn't get there that grew up and why? And so the problem I think that is so obvious to me is that young kids, 5 years old, 7 years old, are incredibly curious. They're asking you questions and pestering you, want to know everything. Okay. Then we get kids that are pretty good that come to Caltech. They don't ask questions anymore. They just want to do their homework. They ask you a question because they couldn't solve the problem. But somehow in the educational system, we kill curiosity. I may be overstating it, but we basically kill curiosity. And we even have a saying, which is detrimental. It's curiosity killed the cat. And that's actually telling you that you don't want to try anything because it's going to cause trouble. And I think if you find what happened with somebody like you or me or Carl Sagan made a statement about this that I can't remember exactly, that somehow by some piece of luck, we evaded of this problem that it got killed. And for me, I've always been really curious. Why did I spend 10 years looking for a magnetic monopole? It's curiosity completely. Why? So to get to where we are, and you don't have to be a physicist, but I think in life we have a real problem. So if I don't just go out in the street now, we live in a society where everybody walks around with one of these cell phones. But do they know what it is, how it works at all? Most people don't have the foggiest idea how it communicates, how it makes little pictures on the screen, what it is. Then they go home and they turn on their television and they have no idea what made the picture there. And they don't even ask why. And then they go in the kitchen and turn on the microwave to cook their dinner. And how many people really have any idea what it's doing to cook their dinner? So we've created a society where people don't even have, they've been killed. They don't have the curiosity that we all are born with. It's such a wonderful human factor. And so we've got to do something about our education system to encourage, not kill curiosity. And to me, that's the message that I think anyone that's curious, it's wonderful, do it. You're not going to get killed.
It's so interesting that you bring that up because there's something I learned, which I attribute to my friend James Altucher, that he quoted when he gave his TED Talk in San Diego. He and I both gave TEDx talks in San Diego. And he quoted that a 5-year-old kid smiles or laughs 300 times a day. But by the time they hit my age or your age, it's down to 5 times a day. So laughter, like happiness, seems to be correlated with curiosity. And it also reminds me of another guest, in addition to James, who's been on the podcast, who was a psychiatrist. His name is Dr. Judson Brewer at Brown University. And he looks at ways to overcome addiction, such as smoking, drugs, food, whatever, wherever there's something that the human mind can crave. He feels that in this branch of psychology, that you can overcome the addiction and manage it via becoming curious about the bodily sensations that one is craving. So he says that the first thing you do is become essentially curious.
That's very interesting.
Okay, 7442. Yes. The last question I want to ask you It harkens to the name of this podcast, and it also involves curiosity and imagination. And it's one of Sir Arthur C. Clarke's so-called 3 laws. His first law is that any sufficiently advanced technology is indistinguishable from magic. His second law, which you and I can make good use of, is that for every expert, there's an equal and opposite expert. And his third law is that the only way of discovering the limits of the possible is to venture a little way past them into the impossible. That's, of course, the name of this podcast, the Arthur C. Clarke Center for Human Imagination's Into the Impossible podcast. So I want to ask you, what aspect of life was perhaps mysterious, maybe even intimidating and terrifying to you as a young person, but because of your courage or because of your hard work and discipline, became possible because you went a little bit beyond your comfort zone?
Well, as I said, I think I didn't have a lot of mentoring as a young person, and I also was in over my head. In some sense, kids around me were more sophisticated or came from more sophisticated homes, and so the big problem that I had, although it doesn't show so much now, is being overly shy, if you want. Not shy in the way that you think of shyness, but shy in every aspect of kind of being a person. That I may, in my head, have been very adventurous, which I've always been, and had curiosity, but I was very reticent until I got enough confidence through success, I suppose, to merge later in life. Somehow I'm very lucky that happened, that I went down a path where I succeeded enough that I developed the inner confidence. But otherwise, I think I didn't have the confidence somehow in me to do what I was capable of doing. And that took a long time to develop.
It's funny that you say that as well. I had on Lee Susskind this week, and he basically said the same. He suffered from what people call the imposter syndrome until he was 50, and he was he's a member of the National Academy. And
I still have the imposter syndrome. So the thing, I'll tell you an anecdote from the Nobel thing. Okay, so mostly it's intimidating, of course, to have this king give you this thing, but they walk you up at the very end. When they give you your check and so forth, they don't give you your check. But when you walk up, you go to the foundation, Nobel Foundation, and they take the official pictures of you and all this stuff. This is after the ceremony. I don't remember whether it's the same day, but you go individually. And I went in, and then they hand you this little book, a book kind of like this, not much more than this thing that I'm holding in my hand, which you can't see very well. And but it's leather bound and so forth. And they open it up to a page and ask you just to sign your name. Okay. I'm curious, right? So I look back and I look back, and you look back on the previous pages, and there's, Einstein's signature or Richard Feynman. Yeah. And if at that moment you don't have the imposter syndrome, which I certainly had, how do I belong on this same page, same book? With a finite number of pages and signatures. It's not like, it's a telephone book or something. I think that I certainly have had it, and I had it dramatically at that moment. And
well, Barry, I so appreciate you and all the generosity and graciousness you've shown me personally. You don't have to do it, and yet you do it. There's so much here to talk about your life, and I hope you'll come back in the future. I hope I can pick your brains and I don't drive you crazy with other crazy ideas that interest me, but maybe not interest you. But I want to always thank you for the sage advice. And
yeah, well, I know this one's about you interviewing me, but sometime we have to get together when this pandemic gets out of our way, so you can tell me all about CMB and what you're doing. You can answer your side of the same group of questions, which I'm sure will be different, but very interesting.
It means so much to me. I can do that, Barry.
You
Anytime.
owe me that as payback.
That's right. I'm happy to pay it back, and I won't make you sign any leather books. Barry, thank you so much. Have a wonderful rest of the day and the rest of your week, and I'll let you know when this comes out.
Okay, thanks. Bye.
Any sufficiently advanced technology is indistinguishable from magic.